Okay, so we continue the lecture about Tao's paper, about the Collatz problem. And if you arrive here now, you better watch the previous class, otherwise you won't understand anything I'm about to say. So in the previous lecture, we proved the main result, which was that almost all integers in the log sense, log density sense, attain almost bounded values, in the sense that if you take any function going to infinity and you go through all the orbits of the Collatz map, you see that almost all of them satisfy that the infimum or the minimum number on these orbits is less than this given function. So basically, that's what we showed. If you want to see more details, go to the previous class. And then we proved that condition to a proposition that we will prove not in this class, but in the next class. Okay, in this class, we'll prepare some background and we'll lay some methods so to help in the next classes. Okay, so our goal now is to prove the proposition, which was proposition 24, I guess, from the previous class. And for that, we will need some tools, and that's what we do in this class. Okay. Okay. So first, let's start with a definition, which basically just recalling what is an independent and identically distributed random variables. So we say that x1 and x2 up to xn are IID, which means independent and identically distributed random variables if, well, they have the same distribution, and they're independent in the sense that if you do the probability of x1 belonging to a certain set S1 and the dot xn to a certain set Sn, that is just a product of the probabilities. Okay. And a disclaimer. So we have a bunch of different. So we'll have to take some norms of some vectors from now on. And in Tao's paper, he doesn't make any comment about which norm he's taking in each place. And you have to figure out what his meaning by each time he does that. So I want to be clear about this. So if you take any vector, let's say x, and the norm p is just, you take x1 to the p, and you add up 2xn to the p, and you take 1 over p. The infinity norm is just the max of the entries to n. So we'll make the convention here. Okay, so we use the convention that this norm without any sub just means the one norm, okay? Which means it's just the sum of the moduli of the variable of each entry, okay? And whenever I use any other norm, I will explicitly say so. Okay, so that's the convention. Okay. So now I will prove a bound. So I want to prove a bound which is purely in probability theory. But before I do that, I just want to recall some known easier bounds. So for instance, we have Markov's inequality or Markov's bound, which is the probability, and there is a typo here in my notes, the probability of x being greater or equal than a is less or equal than the expectation of x divided by a. And let's assume that x is r plus valued. So usually this inequality is stated with moduli of x. Okay. Yeah. So maybe we should state it like this. Okay. So now this could be RD valued. Okay. And we have what's called Chernov's bound, or Chernov's inequality, which is a clever way of using this, is will the probability of moduli of x be greater or equal than a equals the probability of e to t moduli of x be greater or equal to e to the ta. So Chernov's bound is actually without the moduli. Okay, so suppose that x is just r valued. Let me see. Suppose that x is r valued. I mean, you could do the same thing with if it's not, but anyway. Then you could do that, or you could. I was doing with the moduli. You could do that as well, but let's state it like this. Equals that. So now these are two positive things, and we can apply this bound here, and then we have. And the idea is that maybe you get a better bound for this if we choose a parameter t which is nice. So you produce something which is small here on the right hand side. Okay. But you could also do with the moduli. Okay. So now what I'm going to state here is an analog of Chernov's, at least in the eyes of Tao, it is. And I can see why he thinks it is. Bound. So I'll have x, so let x be a random variable, zd valued, and assume two things. The first thing is that the covariance matrix of x, which is just the expectation of xi times xj, ij from 1 to d, where x has coordinates x1, x2, xd. This is positive definite. Which means that there is some C positive that covariance matrix of okay. And I would do another convention here. And maybe I would use this convention throughout the whole series parts of this lecture, is that whenever you see C is a small quantity, small positive quantity, that can vary from line to line. So that means that, well, you're seeing some C here, maybe you see a C later, they maybe are not related, but this just represents small quantity. They can depend on some other objects that I'm defining here, and whenever this dependency is important, I will say. And assume that we have the following tail bound, so this is a tail bound. It's an exponential tail bound, which the probability of x being greater or equal than t is less or equal of less than e to the minus c naught t for all t greater or equal to 0 for some c naught positive. Okay? So maybe using the convention already, you can drop this thing, just to see. Okay, so we have this following tail bound. Then what I want to do now is to estimate if I take n copies of x, which are independent and identically distributed to x, what happens with the probability of the sum of these random variables. So let y1, y2, yn be id random variables, all identically distributed to x. Then bound 1, the probability that the sum equals some vector L. So maybe another convention here. So maybe that was convention 1, and that's convention 2. Let me put here convention 3. I will try as much as I can to use arrows for vectors. Sometimes I will forget to put arrows. For instance here, these guys are vectors. I'm not putting arrows, just because they are a random variable, then I want to put arrows in a random variable. But whenever you have a vector, I should put an arrow, okay? So this probability is bounded by a constant. It can depend on the dimension and a sum function, and I will say what it is in a moment. And second, that the probability of... So this is saying what's the probability of this being something. So basically is a certain function, which represents a certain decay of this something compared with the average. So this mu here is the expected value of x. Okay, so n times mu is the expected value of the sum of the y's. So if you compare this L with the expected value, you have a certain decay. And I will say what this function gn is in a moment. And then if you want to compute what's the variation, so you compute the probability that this is t away from the expected value of the sum, that is, oh, there is an n to the minus d over 2 here, sorry. And this is compared again with a constant that depends on d of gn of c t. And gn here of x, this is e to the minus x Euclidean norm squared over n plus e to the minus again here Euclidean norm. But this norm here, for instance, the 1 norm, because by the convention this is supposed to be the 1 norm. Okay. So this is the part that you can get confusing in his paper, because it doesn't put what the norm should be here, but he definitely wants the 2 norm here by the proof he gives. But in here, he definitely wants the 1 norm, because he will use this proposition with the 1 norm. So you have to be careful. Here is 1 and here is 2. Okay, so the proof, let me erase this part here. So proof. So first of all, problem. Show item I implies item 2 by estimating. So here I'm giving you a hint. So, well, you want to estimate this. So the probability that y1 plus yn minus n times the average, I should put it right here, greater or equal than t, equals basically just the sum over all the l's, such that L minus n mu is greater or equal than t over the probability that y1 plus yn equals L. Okay? And these probabilities we can estimate by this. So if you use this bound, then you have to estimate the sum. And to estimate the sum, you can use the integral test. You just estimate the integral over the same region. And to estimate the integral, you just integrate the thing, and you realize that this n here will come out, will be cancelled by the integral. You just have something like that. Okay? So this is kind of a pretty standard. So only will show item I. Okay, and to show item I will use what's called the Fourier method. Okay, so I will define this random variable, which will be this guy here. Or maybe I shouldn't use the same t. Well, I'll use t here as a vector, that t here is another t. And where, what I mean by this is, this is the average integral over the torus. Okay, so what you realize now is that this new random variable is exactly 1. So this integral will always be 0 unless the sum of these vectors here equals L. And if that's the case, the integral is 1. Therefore, y, so this is simply the indicator function of the event that the sum equals L. Okay, that's the function. Therefore, the expectation of W is exactly the probability of y1, yn equals L. Okay, so, and what is the expectation of W? Well, the expectation is linear, which means that, and the integral here can be seen as a continuous sum, let's say. So you can commute the integral and we leave that as a problem. Maybe I should put it like here. Leave that as another problem. To show that we can commute. Okay, but these variables are independent, therefore, and this is a product because this is e to y1 times e to y2 and so on. And since they're independent, the expectation of the product is a product of the expectation, even when you evaluate a function on them. So you conclude that this is equal to, and each one of them is identically distributed to x. So this is just ix t to the n e to the minus I l t et. Okay. So problem. Let m of z be this function. because I'm taking the expected value here. Okay, so show that M is well defined if, and I have to be careful here, so since this is norm 1, I have to put here if the real part of Z infinity is less than C naught. Okay, and analytic there. So of course you have to use this bound to show that this is well defined in analytic in this region. Okay, and if you want a hint, basically, well, to show that it's analytic is another ball game. You can either use Morera's theorem to show that it's analytic in each variable, or either just try to differentiate this exactly, and then you show that you can differentiate. So maybe you have to use the denominated conversion theorem to show that, for instance. But anyway, the analytic part is up to you. I will give a hint for the other part. Basically, you just have to estimate that this is finite. Okay, but this is less or equal than expectation of e to the real part of z infinity times the norm 1 of the variable x. So if you use the layer cake, the composition here, this will be just the integral of e to the t real part of z infinity times the probability of moduli of x being greater or equal than t dt from 0 to infinity. Okay. Okay, and then you use the bound. This is not supposed to be C. Right? Change that to C. Okay, so C. Okay. In the end, you only need this to be true for real parts sufficiently close to 0. So if it's a C, it's okay. And that's the problem. Okay, so if you show this is analytic, then you can realize that EW is just MIT to the n e to the minus I t dt. And then now I can make a counter shift. Well, because, I'm going to explain this in a moment. So I can make the following counter shift. And this is supposed to be IT plus lambda. Lambda here is just a sufficiently small vector so as long as it's less than c, this is the real, as long for, let's say, lambda with infinity norm less than c. As long as it's sufficiently small, this will work for the argument. But in any case, that's the bound. So for instance, if the moduli infinity equals c over 2 should be fine. And why we can do this is just because it's a simple picture. Maybe we can do it even here. So imagine that d was 1, for instance. So here we have the torus pi d, and here we have the torus pi d minus I lambda. So if it was in dimension 1, this would be just the interval minus delta to delta, and this would be the interval minus delta minus I lambda to delta node, pi. Minus pi to pi, and minus pi plus minus I lambda to pi minus I lambda. So that would be the integral. And why this integral here equals to that integral? Well, first of all, this path here and this path here start in the end in the same point. So the integral here equals to the integral here, but the integral there equals to the integral here, because because the function is periodic. So this is to the n, this is to the n. Sorry. Well, because m of I t plus an a equals to m of I t if a is an integer vector. So since it's periodic, the integral here equals an integral there, therefore the integral here equals the integral there. And I can do this whenever the lambda is sufficiently small. Okay. Let me erase the other part. And now comes the final problem. Which is show that m of z equals e to z mu plus a half z covariance matrix of x z transpose plus O of moduli of z squared. And this I could put any kind of moduli, because if I change from one to the other, I would just be multiplying by the dimension, which is d. So I want to put the norm 2 here, just to make things easier. Yes. The idea to show this is just to expand this thing in a Taylor series. And once you expand this thing in a Taylor series, you can see that that Taylor series can be comparable to the Taylor series of this. And the difference would be just something like O of e to the mode O of z squared. Okay? So there are some calculations there to do. So in particular, what we have is that if lambda is sufficiently small, so for instance below c and even smaller, then m of I t plus lambda will be a real vector, is moduli is e to lambda mu minus some c t squared plus O of, and these are norm 2. Okay, that's the problem. So to derive this from this is easy, and this requires some calculations. Okay, and this C here, of course, here is related with the fact that the covariant matrix is positive definite. So that's the known degeneracy condition. Okay. Okay. What else? So if you do this, we can simply apply the problem to this, whatever it is, to this identity here. So just replace it by here and put together the terms. You get that this is this e2 minus lambda dot L minus n mu minus cn moduli of t squared. This is norm 2 plus O of n squared dt. And this O of n is just something about it. We'll just replace it by some constant a. Okay. Okay, so this holds whenever, so if is small. Okay. Okay, yeah, yes. So this has to be true if there should be a term O of t squared here, but I'm assuming that this is bounded because I'm integrating in here. So I'm assuming that this thing here, let's say norm infinity, is bounded. So I'm assuming that it doesn't matter really. I'm assuming that this norm here is O1. Which would be the case because we're going to use this estimate inside an integral when t belongs to a bounded region. Okay. Otherwise, if I don't put this, I have to put the O of t moduli of t squared here as well. Okay. Maybe moduli of t cubed here because this square is already here. So yes, great. So I have this bound. So again, limit is just an auxiliary quantity to make this work. So then we conclude that this is, so I can integrate now, and then that's why this n comes here, because if you just do a change of variables to a scaling change of variables, you just multiply this tori by square root of n and integrate a Gaussian, which has its finite mass on the whole thing. So basically we just get n to the minus d over 2, and the functions again. So here, so the problem is by choosing by taking, I guess it's lambda equals to either some, let's say epsilon something small is L minus n mu divided by, this has to be less or equal than 1, so let me put the max between so yes, of moduli of n minus n mu and I guess it's n. I think that's the choice you have to do. So it's definitely yes. So this is the number which is has moduli. Oh, and this is supposed to be norm 2. Sorry. Yeah, this is norm 2. So here it's supposed to be norm 2. Okay. So this is a number which has moduli norm 2 less than epsilon. It's a NRD, therefore its norm infinity will be also small with a constant only depending on d anyway, which is allowed if epsilon is small. So for small epsilon, positive, show EW, and there may be something depending on d in here anyway, but we don't care, n minus d over 2 gn of gn of c and moduli, oh sorry, c and moduli of this, which is L minus n. Oh, sorry. Yeah, I guess, yeah. So I guess it would be better if we define Gn. If we define Gn just for real variables, really, Gn of r is just e to the minus r squared over n plus e to the minus r. And whenever I use it, I put a moduli anyway. I think that would be better. Here. So this is supposed to be, yeah. But in any case, the way I define, I'm taking norm 2 anyway, so I define it by taking norm 2 here and norm 2 here. So then it's correct. Okay. So that's the problem. Show that by taking lambda like this, yeah, for instance, if this guy here is greater than n, then I should just take this thing here. So if I just take this thing here, the moduli of lambda is just epsilon squared. So you get an epsilon squared here, and in here you just have the moduli of this thing, okay, multiplied. So if epsilon is small, then you get the correct thing. Okay. Yeah, if epsilon is like 1 over n, for instance, then you get it with an absolute constant, and if it's the other way around, then you get an n here, and you see that n will still be there, because when you put this thing here, we have a square divided by n squared, so 1 cancels, you just have 1 over n, okay? So you will see that that's the proper choice. Okay, so that finishes the result, because if you just use the problem, then we get the bound. And so this proves 1. And 1 implies 2. Okay. Okay. Okay, so now let's go back. So this was a pure probability bound. Let's go back to the Collatz problem. Okay, so we need some definitions before the next level. So let me define this affine. So Tao calls this A like AFF for affine. So we just use A. It will be this function 3n plus 1 divided by 2 to the A. And then we define this for n odd. Okay. So for instance, if n is odd, then 3n plus 1 is even, and therefore I can divide at least by 1 power of 2, so that's 2, but maybe this is not a number, so you see that, an integer, sorry, so you see that AA maps the odd integers to z a half. We're just adjoining a half to the integer, so this will be a ring when you adjoin this a half here, okay? So this guy is just m divided by 2 to the a, where m is an integer, is a is greater or equal than 1. Oh, greater or equal than 0, sorry. Okay, so that's the map. And if a is a vector, let's say a1, a k, then I can do the same a of n, but you just compose, so you you first apply A1, and then on A1 you apply A2, so that's the so maybe the better way of writing this is with a composition notation. Okay. So in a sense, we are if you remember Crandall's talk, which I think was the second lecture, he defines analogous functions maybe in the opposite direction, maybe trying to invert the Collatz map instead of trying to compute it forward. But in the same way, it's very related. So a second definition would be, so if you give me any vectors, it could be of any size, I will always write B, so it would be something like B1, B2, dot, 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 and I don't care where you finish. I will write Bij to be the partial sum of the coordinates, okay? That's what I would do. The other definition is this function Fn, which will be a function from again from what vectors? This will be a function from Zn to again Z a half, and Fn of a vector will simply be the sum from I equals 1 to n of 3 to n minus I to the minus bin. Okay, using the previous convention. Okay, so from this convention, if maybe it's worth a note, and Tao uses this all the time, if B is, let's say, only have positive entries, okay, no negative entries, or positive doesn't matter, then B1D, which is the dimension of B, is just the one norm of B, okay. Maybe that's an observation. Okay, so we use this thing all the time. Okay. Another definition, which is the an of m. So if you give me a number m, this would be nu2 of 3m plus 1, and then u2 of 3 of s of m plus 1, and so on, up to nu2 of s of n minus 1m plus 1. So what is nu2? Just to recall, nu2 is actually defined in the wrong way before, then I corrected in the previous lecture. Nu2 is just a map from the odd numbers to the negative integers, so that so positive integers. Z plus for me is 1, 2, 3, 4, 5, etc. That takes which is so nu2 of n, if n is odd, is the largest a, so that 2 to the a divides n. Okay. So basically here it's just so what's the Syracuse map, which is the speed up Collatz map? We'll just multiply a number by 3 and add 1, and then divide by the largest power of 2 that you can. So this is collecting the first of these guys. So for instance, you know that s of n equals, if n is odd, is just 3n plus 1 divided by 2 to nu2 of 3n plus 1. So the first entry here. So the second entry will be, again, So if the second entry would be 3 of Sn plus 1 divided by 2 of the second entry of the vector, so it would be let's see, an of maybe this is a2 of n, okay, and then the second entry, let's say the second. Okay, so I equals 2. Okay. In any case, I already did this in the previous class. This is just recalling. And then I will use aij of m by this convention here. This will be the sum of the entries of the vector A. So it will be L from I to J of nu 2 of 3s L minus 1 of m, yeah, from I to J. So that would be just the partial sums of the I entry up to the J entry of the vector an of m, okay. Yeah, and when you do this, n doesn't matter anymore because this is a function for itself. It doesn't depend on n because you can do that for any I, any j. Okay, so that's the definition. Okay. Now we state a problem, and this problem is very similar to the stuff we did in Crandall's, if not some parts identical to the stuff we did in Crandall's paper. So I will leave as a problem. So problem. For every m odd, there exists a unique b in no negative positive integers, so that a b of m is odd. Okay, so for instance, if you start with one guy only, yeah, so maybe I should put it here like D, and then put here N. So if D equals 1, well, this number is odd, so you have to divide by the largest power of 2, otherwise you still get an even number. So A1 is completely defined, and once you have an odd number, then the next guy is going to be just starting point with this one. So if we start with this number here to compute what B2 is supposed to be, well, there is only one choice for B2 anyway. So in any case, there is always one choice for the vector. So the vector is unique, and from that you can also deduce that once you have defined the first, let's say, 10 entries of B, then the 11th one is completely defined by the first 10. I mean, given the first 10. So in particular, for any given number, n odd, this is supposed to be n, B is completely defined. So there are two ways of seeing this. Okay. So there is only one, such that this is odd, and this B is exactly the vector A, let's say AD, because I'm D here, so AD of N. Okay, so it's exactly this vector here we defined. It's exactly, well, obviously, this is more or less obvious, and show that then let's say SD of N equals AD of n applied in n, which is also equal 3 to the n, 2 to AD of n times n plus FD of AD of n. Okay, where f is this function here. Okay, so in the same way, this is a formula for computing. The same way we did in Crandall's paper and also in Terrence's paper. This is a formula to compute the d-iterate of the Syracuse map. Okay, so I'll give you this as a problem because we did something very similar for Crandall's paper. Okay, so proposition 26. Is this 26? Yes. Yeah, the previous was lemma 25. I hope I put 25 in there. So let x be an odd valued random variable, and let m be greater or equal than 2 plus c times n. Again, the same convention. C is just some small quantity, positive quantity, and assume the total variation. So I've defined total variation in the first lecture, in the very first part there. So if you don't know, you should take a look. It's basically just comparing the probabilities what in here with the stuff in there. And this can depend on this C here. Then the total variation of A and X geom 2n. This can depend on that C. And this is another C. So this C maybe is not equal to that C, and this C is that C there. Okay, so let me drop this dependencies in C. So this thing can depend on how small this is. So let me keep this C here. And maybe since I'm using the same C in 2 lines, maybe I should put here a C1. Okay, for some C1 positive. Okay, so M and N are fixed. Okay, what I'm just saying is that suppose I have a certain bound with some constant here that depends on C, then the same constant that shows up here can be manipulated and appears another one here, also depending on C. But now this thing is just so minus C1n, where C1 depends on C. It can depend on C as well. Okay. So basically, whatever you put here, there is a function that puts a constant here, and there is a function of C that puts another constant here at C1. Okay. It's another way of saying that it's a weird and nice way of saying that whenever you have such an estimate, you can manipulate this estimate to create another estimate like this, and there is some relations between the constants which are explicit in this less curly notation. Okay, so what the lemma, the proposition is saying that the following. Well, first of all, I have to define what this geom is and what this unit means. So let me define that first, and then I will try to explain the idea behind the proposition. So what's geom? Geom 2 is just a distribution over the just a random variable that is z plus valued. So again, z plus for me is 1, 2, 3, 4, 5, 6, 7 positive integers. And with the probability of geom 2 equals, so let me say geom to the n is z plus n valued, with the probability that this equals some vector b is just 2 to the minus the norm 1 of b. Okay, so it's just a geometrical distribution. If this was the integers, it would give weight half for 1, it would give weight 1/4 for 2, and it would give weight 2 to the minus n for the integer n. Okay, and this is just a high dimensional version of geometric distribution. Okay, and what is what? What is uniform? Well, this is basically obvious. So this unif is just a uniform distribution over the odd residue classes mod 2m. Okay. So basically, what you can just think of just the numbers 1 to 2 to the m, and the weight you put for any of these numbers is just 1 over 2 to the minus m. Okay. Okay. So what is this proposition is saying? This proposition is saying that if x is close to be uniformly distributed modulo 2m, okay, then when you take these powers here, these coefficients of the powers of 2 that you have to divide the numbers to be able to compute the iterates of the Collatz map, this guy is close to be a geometrical distribution. Okay, so if you're randomly taking integers on that are uniformly distributed modulo a certain large number, so 2 to the m, then this guy is close to be geometrically distributed. So this is an heuristic that the way we define these guys here. So it's a way of, this is a way of trying to measure, trying to bound this thing here in a way. Okay, and one way of doing this is to compare these numbers here, so this is A of D, with a certain known distribution. Once you condition n to be uniformly distributed here, modulo 2m, then you could say that this A is here geometrically distributed, and then you can use that to create a bound for these guys here. Again, in the probabilistic sense. So that's the heuristic behind it. So what Tao wants to do is to get a hold of this right-hand side here, and this is one of the key parts. Okay. So what we do is just, we will finish, we will prove, it's not too long. We will prove this proposition and we'll finish the class. So maybe I want to leave this proposition here. So let me erase everything but the proposition. Okay, so how we're gonna do this? Oh, and it actually gave some wrong explanation. The uniform distribution over the odd residue classes puts weight 1 over 2 to the m minus 1, or not 1 over 2 to the m, because I'm only considering the odd number, so I have to reduce the 1. Okay, and that will be important later. Okay, so just to be clear, what I mean is that the probability of the unit of odd 2 to the m equals some number, let's say L, is just 1 over 2 to the m minus 1. Which is that 2 to the n minus 1 is exactly the quantity of the residue classes here. Okay, so let me erase that. Let me leave that for a moment. Okay, so let's start the proof. So what's step 1? So step 1, so I want to measure a total variation, okay? So in particular, I want to know I want to compute the probability of this thing being equal to something minus the probability of this thing being equals to the same something. And I will summate over all these numbers. So this is a vector. This is a vector. So I will compute the probability of this being a certain vector minus the probability of this being a certain vector, and it will summate over all the vectors. So what I can do is I can just truncate. I take all the vectors with the norm less or equal than something plus the rest. Okay. So then the rest will be bounded by the probability of this, the norm of this being greater than something, plus the probability of norm of this being greater than something, which will be the tail of this total variation estimate. So first I want to bound that tail. So that is, I want to, so let's say bound the tail for A. So first I want to study this. So I have a claim. So we claim that probability of an x be greater or equal than some m is 2 to the minus cn. Okay, that's the claim. Again, maybe the c is not the same c here, maybe not the same, it's just some small whatever. Okay. So this is me estimating the tail. There will be part of the computation of the total variation between A and the geometric. I don't have to estimate the tail of the geometric because the previous lemma will give me that for free. I will mention that later. Okay, so how can we do that? Well, one nice way of doing this is, so these guys are always positive. So this thing is just a sum of the entries of the vector. So one thing is that to write this thing as just a sum from k equals 1 to n minus 1 of the probability that A, and then I would turn to that partial sums is less than m, which is less or equal than a1k plus 1 of x. Okay. So this is a sum. So you take the partial sums, and exactly one of these partial sums will be less than m, while the next one is greater or equal than m. Okay. So basically what I want to do now is if I can estimate this quantity, so basically I want to show, so it's enough to show that let me see if it's recorded. Yeah, still recording, so it's enough to show that this probability here is of the same form. For k less or equal than n minus 1. Okay, because if that is true, then I can summate all of this, and we'll just be multiplying this term by n. Then I can just maybe pick a smaller c here, and then just swallow that n into the explanation. Okay, so that will be enough to show. So what we're going to do is this: whenever you have something like it's hard to compute, I mean, you just open the thing as much as you can. I mean, at least that's always a good strategy, and then you see how the parts interact. So maybe I should put, yeah. So I'm considering the vector b, maybe I should put it like this. Yes. And here I'm using again the convention. And here I just have to put the probability of a, let's say, in this case it's just ak plus 1. So let's say k plus 1. I want to put k, so let's put ak of x equal, so let me put in the previous form. Let me put it like this. And I'm just considering here, when I'm doing this, so maybe I should put like this. Yeah, just to be completely rigorous. This is 2 to the m. So the probability that this is equal to b, and then that the final guy here is equal to something. Let's say k. Since I didn't define, so I will make a trick here. Like say this will be k plus 1. K plus 1 of x equals bk plus 1. Is there anything else? And x being congruent to theta mod 2 to the m. Yes. Okay. And this is supposed to be theta odd, of course. So there is a time for here. Okay. So that's what we summate, because, well, a has to be something, ak of x has to be something, and the next one has to be something as well. So I'm summating over all this, and theta can only be in one residue class modulo 2m. This is m. It can't be any other. So that's the sum of the probabilities, okay? And it turns out the following. Because of the previous problem, once I give b here, bk plus 1 is completely defined, because it can only be one guy, okay? So there is only one possibility for a k plus 1 x equals to bk plus 1, because this is completely defined in terms of the previous b, because of the lemma. So once I know this, I know what there is only one possibility of bk plus 1, exactly one. Okay. So once I give a b here, bk plus 1 is completely defined, and the claim here is that also theta, there is only one residue class that given b that x can be. If that is true, then for each b here, you would have possibly a sum over the bk plus 1s and the thetas, but you don't, because you just have 1. All other probabilities are 0. Okay? So if that was true, if that's what I just said was true, I could just bound this thing by the sum over all the b's, such that the probability of a k of x equals b. Okay? Yes, I could do that. So my claim here, so let me write here, so by the previous problem, once b is given, bk plus 1 is completely defined to be the only one such that a b bk plus 1 of let's say x is odd. So imagine that I fix the value of x to be something. Okay. So once you have that, so given a b, there is only one bk plus 1 such that this is odd. So this is the first claim that I say. Once I give b, bk plus 1 is completely defined. So all the other possibilities for bk plus 1 can't be chosen because the probability of that will be 0. Okay. And moreover, we have this. And because of that, if you do the calculations, you have that b1k plus bk plus 1. So let me write this up to bk plus 1. sk plus 1 of x equals 3k plus 1 of x. Again, just using the formula from the previous problem. Right, from 1 to k plus 1 of 3k plus 1 minus I and 2 to b1 I minus 1. And since I multiplied everything by 2k plus 2 to the b1 k plus 1 appears like this, okay? So it's the only one, so bk plus 1 is defined as the only one that this guy here is odd. Well, so this guy here is odd, so you multiply. So you see that this side here only depends here, only depends on b here, because of the way the sum was built. So therefore, this side here only depends on b. And this guy here is odd. So you can see that the choice of this being odd, bk plus 1 to be the unique guy that this thing here is odd, is exactly the same as asking by this calculation here that this thing here is equal to an odd guy times 2 to the b1 k plus 1. So we conclude that that bk plus 1 is uniquely chosen so that this number here on the right, 3k plus 1 times x plus the sum of I equals 1 to k plus 1 of 3k plus 1 minus I, 2 to the b1 I minus 1, and of course when I is 1 is b1 from 0, the convention is that that's 0, so we just have a 3 to k plus 1 here. Is that, so this should be congruent, to an odd number modulo 2 to the b1 k plus 1. Another way of saying this is that if you just add b1 k plus 1, that's congruent to 0 mod to the 1 plus b1 k plus Okay. So this is another way of choosing bk plus 1. But then you see that if that is true, then x, since 3k plus 1 is always invertible modulo 2 to the L for any L, you see that x has to belong to be congruent to some theta which will depend on b, because this side depends on so if I take modulo b1k plus 1, then that is 0. Yeah. Okay, so you conclude that this guy should be congruent to something. So maybe yeah, that is true. So in particular. So bk plus 1 is chosen in a nuclear way by this equation, but in particular, if you take modulo b1k plus 1, we conclude that x is congruent to a certain thing which depends only on b, which goes only from 1 to k, of mod 2 to the b1 k plus 1. That is, there is a unique odd residue class that x has to belong modulo b1 k plus 1, because you have to just take modulo bk plus 1 here on both sides. Well, this is 1 plus bk plus 1 implies that this thing here, so this thing here is congruent to 0 modulo b1k plus 1. In particular, you can invert, because 3k plus 1 is always invertible modulo any 2 to the L. And then x has to be congruent to a certain particular class modulo b1k plus 1, which implies then that, well, bk plus b1k plus 1 comes from here. Well, that's what I want. And so this is b1k plus 1. This guy here is greater or equal than m, so it implies that x has to be congruent to a certain particular residue class mod 2 to the m if m is less or equal than b1k plus 1. Okay. So what I'm saying here is once b is chosen, then there is only one option for bk plus 1. And there is only one option for a residue class theta modulo 2m, as long as m is less or equal than b1k plus 1, which it is the case in this summation. Okay, so once you choose b, all the other guys are defined. So in this summation here, once b is chosen, there is only one term that is non-zero. Okay. So we conclude that the probability of akx, 1kx is less than m, less or equal than 1k plus 1x is less or equal than, so I can summate over all the b's. And there will be only one choice, then that will be equal. And then here, there will be only one choice for the other guys. Okay, exactly one. At most. So, at most, because maybe there isn't the bk plus 1 doesn't satisfy this anyway. Well, maybe this probability is 0. In any case, there is at most one, there is non-zero, and then we have to compute this probability here. But this probability here will be bounded by just removing this condition and this condition, just staying with x congruent to theta modulo 2m. So we just do that. X congruent to theta mod 2m. Okay. So for each b, there will be one congruence class modulo 2m for each x has to belong, which is this theta b, which is coming from this this thing here. Okay. And we know that b1k has to be less than m, so let me still use this condition, which is b1k being less than 1 is just another statement for the norm of b being less than m. Okay, of this. So then you conclude this. Great. But what this probability is, well, this is the probability of x modulo 2m be equal to something. That random variable be equal to something. But its total variation is equal to this. So it's close to this. So this would be the same thing. So let me use let me use a smart Let me use a smart board here. So this thing will be equal to the probability of the uniform distribution being equal to a certain theta b plus O of this. Okay, because of this bound. Okay, and this probability here is just 2 to the 1 minus m, which is comparable just to 2 to the minus m. So we conclude that this thing here is less than another smart board, and then you have just 2 to the minus m. And then you can make a sum here, and it's easy to compute the sum. This is equal to m minus 1 and the number of variables, k. Okay, so let me just state the problem. So we're almost done. Where is my list? Here, almost there. So problem. So basically here we just use the property that for a sub n of x be equal to a certain vector, the solution to this equation lies in one residue class. So the solution of this equation for x is exactly one residue class is the solution. So the solution is one residue class mod 2 to the minus b 2 to b plus 1. That's what we did. Is exactly which is what this is saying here. Okay, so using that we were able to, from this bound, to derive this tail bound here. Okay, so to finish, I want to summate that. So my claim is that this is less than 2 to the minus cn, and that will finish the claim of step 1. So because that was exactly my claim, because we showed that to show the claim we only need to estimate this, and this proves the claim. And the problem here is use Stirling's formula, which is the n factorial is asymptotic to e to the minus n square root of 2 pi n to the power n, to show show that if k is less or equal than n minus 1 and m is greater or equal to 2 plus c n, then 2 to the minus m m minus 1k is something that can depend on the c here, 2 to the minus c1n, or c1 can depend on c. Okay? It's also a small positive quantity. Okay, so that's the problem. It's not hard to show. So that finishes the claim of step 1. So let's go to step 2. So step 2. So from step 1, we know that the probability of a and x being greater or equal than m is 2 to the minus c. 2 to the minus c. Yes, that's what I want. Okay. For some constant c. And then we have to use that. So now let's estimate the total variation. So it's exactly as I said, the total variation between these guys would be a sum of the probability of geom of 2 equals some vector n, some vector b, minus the probability of a and x equals some vector b moduli. Okay, and I'm just made over all the vectors z plus n. Okay, so then I separate in two cases, the ones which are less than m plus the ones which are bigger than m, bigger or equal than m. But that one, I use the triangle inequality in these two terms, then I add up, this will be exactly equal to the probability of geom of 2 of n being greater or equal than m, plus, so this will be a lesser equal probability of an of x being greater or equal than m. Okay. Which are just estimated. Okay. So this term here is O of 2 to the minus Cn. Good, because that's exactly what we want to prove here. And this term here is by the previous bound. So this is by Chernov's type bound lemma. You can show that this is O of 2 to the minus Cn as well. Or you can either do by brute force, you can actually compute this by brute force without using the lemma and show this as well. Okay. So this whole thing here is O of this, so I can again, using a smartboard, that this is just O of 2 to the minus, well, I can even put like this and make here a 2 to the minus Cn. Okay. Now we just have to estimate this sum. Well, this probability we know. This is exactly 2 to the minus 2 to 1 minus moduli b. Oh no, this is just moduli b minus moduli b. The other was the other. This is just that. Okay. Okay, so now I just have to estimate this. So what's the probability of an of x equals some b? But then we realize something. It's exactly this computation here. There is a map. An of x equals b. This is exactly this computation. It can be solved exactly when this. So again, this was the claim before. It's exactly solved if and only if x is congruent to some theta, which will depend on b, mod 2 to the b plus 1. Okay. the solution set for x of the odd number is exactly a residue class modulo 2 to the beta minus 1 plus 1, 2 to the modulo b plus 1. And that's exactly what we did here. If instead you replace k plus 1 by n, this will be exactly this thing here. So there will be plus 1 here, the plus 1 here. Okay. So it's exactly one residue class modulo b plus 1. It's just one thing you can derive from that problem I wrote about the affine maps and the identity with the iterates of the Syracuse map, etc. In particular, this is exactly the probability that x is congruent to some theta b mod 2 to the b plus 1. Okay, but we know what this is because this thing here, let me put this plus 2 minus cn, because this thing here is estimated by this. Because of this total variation, this will be identical to the distribution, uniform distribution of the odd residue classes here, which will be just minus this, plus a O of 2 to the minus m, 2 to the minus, 2 to the minus m. Well, this would only be true really, so here, this thing would only be true if the moduli of b was m, exactly m, if one moduli of b plus 1 was exactly m, then I could apply this bound here exactly. Okay, and that would be it. There would be 2 to the m here. Even. Okay. But maybe it's not. The only thing you know is that 1 plus b is less or equal than m. Okay? So let me erase this thing. But again, from this you can derive that. So my claim is that if this is true, which it is in the sum we're making, then that is equal to that can be estimated like this. And it's basically a simple computation. So basically to show this, I need to show that yes, what is this? It's here. So basically if L is less or equal than M, so L will play the role of 1 plus moduli of B. So yes, if L is that, then the total variation of uniform on 2 to the LZ with X mod 2 to the L. So observe that the assumption in the proposition is that we just have two numbers m and n greater or equal than 1 satisfying this. I'm not saying that this holds for every m from 1 to again, I'm not saying that this holds for several tuples of m and n, just for two fixed numbers m and n. Okay, but this implies something still. So basically, what you can do is that, so maybe that I would put that as a problem. It's in my notes, the solution anyway. Problem. But you can think without seeing my notes. If L is less or equal than M, so under the conditions of the proposition, if L is less or equal than M, show that this total variation is less or equal than the total variation of unif on 2 to the m z and x mod 2 to the m. And we know that that's 2 to the minus m. Okay. So for every LS, I can compare, and L will be this guy plus 1. L will be moduli of B plus 1, so I can put L here. okay, because this is bounded by this. Okay, so you have if the thing is close to be uniform in a very large residue class, so then for the other smaller residue classes, it should be more or less the same, and it is. Okay. In particular, since you can put M here, you can also put 2 to the L, so you get the exact same bound with L if you wish. But we're going to use with the minus M, which that's what we need. Okay, so yeah, so that's the problem. So if that is true, then what I did here, it's indeed possible. So then I can replace this thing in here. So then we conclude that, so let me, yes, the total variation of geom 2 of n and an of x loses to the summation of the b's, which are less than m, again, positive integers, vectors. And if I replace this in here, we get just O of 2 to the m, so I get just 2 to the minus m. And again, this is the summation we did. This is 2 to the minus m, m minus 1, and in here we have n guys, n things. And again, we estimated this when k was less or equal than n minus 1, but if k is n, is the exact same thing. So by the previous problem, this is 2 to the minus some c. Okay, and that finishes the proof. So the key part was just the fact that once p is given, the solution of this is exactly one residue class modulo 2 to the modulo I of b plus 1. Okay, and once you know that you can compare the geometrical distribution with an of x once x is uniformly distributed over the odd numbers, at least if it is in some large residue class. And how large? Well, m has to be greater or equal than, a little bit bigger than 2n. So to that be true. So n is the size of this vector. So if you had a large residue class compared to n, greater than twice n, that will be enough to make this heuristic. The heuristic that if x is close to be uniform over the odd, then anx should be close to be geom 2n. That's the heuristic. And that's proposition 26 is a rigorous statement about this heuristic. Okay, so we'll finish here for today, and then the next lecture I will use proposition 26 plus some other proposition, which I will assume, to prove proposition 24, which was what remained to be proved in the last class. Then we will have another proposition to prove, and so the next class I will do the same. I will prove that, assuming another thing, and then you remain this another thing to prove, and then the final class, which maybe will have 2 parts again, I will finally prove this this new proposition, and then finishing the argument. Okay, I hope you enjoyed. See you next time.